What even is electricity? Most people have no idea what electricity is. Here's what they do know. In the morning, you load up your coffee machine, you push a button, some magic happens, out comes coffee, and you're no longer cranky. That's it, right?
Wrong.
You can totally learn how this magic works. Electricity is absolutely critical for making devices like your coffee maker work. But it's very mysterious because, well, we can't see it. And that's why we're going to use something you can see and feel, this balloon, to understand how circuits actually work. So without further ado, let's see how we can relate this to this. We'll start with how a balloon works and compare it to an LED circuit, like the one in your coffee maker. Next, we'll talk about the relationship between voltage, current, and resistance. We'll then see how to read the value of a resistor and find it in our kit. And finally, we'll use Ohm's law the way real engineers do, to choose the resistor that sets the brightness of a light. And here's what you'll need. Resistors, some LEDs, some wire, a breadboard. And this is totally optional, but if you really want to follow along, you can get some batteries and some connectors and maybe a balloon, if you want. It's totally optional, but it's gonna let you really feel the electricity. This is a regular party balloon. If I blow into it, I'm storing air inside. And if I let go of the neck, all the air suddenly rushes out. But why? Well, because air is a gas, and it wants to spread out to equal pressure everywhere. When I blow air into this balloon, pressure builds up. The air is dying to escape to match the outside pressure, but it can't, because I control the only way out. Now, would you believe that a balloon behaves very similarly to a battery? When we charge a battery, we fill it with electrical energy, just like how we blow air into a balloon. Jesus, no. For example, this is a 1.5 volt battery, this is a 3 volt battery, and this is a 9 volt battery. Each one is at a higher pressure than the other, much like these 3 balloons. And you'll notice that batteries have a plus and a minus end. This of course indicates which way you should plug them in, but it also indicates which side has more pressure. The plus side is like the inside of the balloon, and the minus side is like the outside. So this battery is charged. It's got voltage, 1.5 volts to be exact. So why isn't the electricity rushing out of this thing like the air rushes out of a balloon? What's stopping it? Well, electricity can only flow through a material called a conductor. Okay, so logically, to make all this voltage rush out, all I have to do is connect the plus and minus end with wire. And that, my friends, is what we call a short circuit. It's basically the equivalent of me doing this.
Nice.
Basically, all the air pressure or voltage rushes out at once. So you really want to try to avoid short circuits as much as possible, because at best, they don't accomplish anything useful, and at worst, they could really damage your stuff. Or worse, you. So, let's give this electricity something to flow through that isn't just bare wire, and let's prevent that short circuit from happening. So, I'm gonna take this connector and snap it into my 9 volt battery. Let's add some components and build a circuit between the plus and minus ends of this battery. Now we're cooking. The electricity that flows through this circuit is called current, and we measure current in amps. If we look back at our battery balloon, you can think of current as the air flowing out of this balloon. A better way to visualize this current is with this pinwheel. If I let this air out of the balloon and let only a little bit of air come out, the pinwheel doesn't move very fast, which means there's a low current. But if I let a lot of air escape, that's a high current, and it's made the pinwheel go very fast. Now these components are limiting the flow of current and not letting it all come out at once. But what even are these components, and how are they limiting the current? This guy here is the LED. It's the part of the circuit that lights up. It acts as an indicator for how much current there is. The brighter this LED is, the more current is running through it. But the LED is not the one that's controlling the current. That job belongs to this guy, the resistor. Let's explain resistance by coming back to the balloon. When the balloon is full of pressure or voltage, I can squeeze this balloon's neck to determine how much air is going to come out of it. So if I'm squeezing the neck really hard, that means only a little bit of current is coming out. But if I squeeze the neck not so hard, all the air comes out at once, meaning there's a lot of current. Here's another nifty analogy for you. Let's say I have two balloons and one is at a higher pressure or voltage than the other. And let's say I apply the same resistance to each of them. I squeeze the balloon's neck the same amount. The one with more pressure has let more air flow out. So if voltage is high and resistance is the same, then current will also be high. Let's compare this to how my LED circuit works with 3 volts versus 9 volts. I can see I get a lot more current with the 9-volt battery. See how the light is much brighter? Now let's talk about why all this actually matters when you're designing a product. Imagine you're an engineer and you want to design an LED indicator for a coffee machine. Let's say you want it to run off of 5 volts from inside the coffee machine, and you want it to glow softly, bright enough to let you know that your sweet, sweet coffee is ready, but not so bright that it blinds you and ruins your day. To do this, you don't want to just randomly pick parts. You gotta pick the right ones that are gonna make a great product. For my coffee machine, I'm gonna choose a green LED, because green is positive. It means good things, like coffee. So now I got my pretty color. How am I gonna pick the right resistance to get the brightness that I want? This is where Ohm's law comes in. It's one of, if not the most important laws of electricity. Ohm's law states that voltage equals current times resistance, or V equals I times R. V is measured in volts. I, the current, is measured in amps, represented by the letter A. And R, the resistance, is measured in ohms, represented by the Greek letter omega, which is a lot of fun to draw. Okay, back to designing our indicator. I'm gonna use 5 volts from this USB cable to represent our coffee machine. So, just like that, we know the V part of our equation, which is 5 volts. Now we need to know the current, or I, so that we can solve for R, the resistance, and then pick a resistor. Now when picking a current, if I was an engineer that liked to live dangerously, I might just pick a random current, a current like 1 amp, to see what would happen. We haven't really covered LEDs yet, that's in our next video, so let's assume all of the voltage is applied to the resistor, not the LED. So we start with Ohm's law, which is V equals I times R, and we're solving for R, which equals V divided by I. Fix my I, there we go. We know that the voltage is 5 volts, and we're assuming a current of 1 amp. So 5 divided by 1 is 5 ohms. Now I'm gonna continue to be a dangerous engineer and build this circuit on the breadboard and see what happens. And I'm gonna slide these little babies over here onto my face for no reason whatsoever. Don't try this at home. So we have 5 volts. Okay, so this LED is crazy bright and super hot, and it's eventually gonna burn out, which is why I have these glasses on. So I'm gonna stop this now. Why did that happen? Well, it turns out 1 amp is way too much current for a simple LED like this. 1 amp is for something that's way more powerful, like a phone charger, and 10 amps is for something even more powerful, like a hairdryer. A light like this, on the other hand, requires way less current. In fact, it can get into the thousands. A light like this might require like 0.005 amps or 5 milliamps. So, using 5 milliamps as the current, 5 volts divided by 0.005 amps equals 1000 ohms, or 1 kiloohm. Okay, so now we know that we need a resistor with 1000 ohms or 1 kiloohms of resistance for our coffee light prototype. How do we find the resistor with that amount of resistance? In other words, how do you know how many ohms a resistor has? At first glance, this feels impossible. For example, all these resistors that come in the NLab kit are the same size, but they're different resistances. And then over here, I have resistors of all different sizes, but all of these are actually the same exact resistance. They're all 1000 ohms. So how do we tell a resistor's resistance value? We look at their color codes. Resistors tell us their value using these color bands. This is a standardized code that engineers use all over the world. And here is the code. This is the key. Now I'm gonna pick a resistor at random and use this key to determine the color code and thereby the resistance. Picking at random, totally random. Here we go. First things first, orientation. To know which way to read a resistor, look for the gold or silver band. This band is the tolerance, and it always goes on the right. So once you have the gold or silver band on the right, you can read the other stripes left to right, like a book. So this is stripe 1, 2, 3, and 4. Another nifty way to tell the orientation is sometimes the first 3 stripes are in a cluster, with the 4th one kind of hanging out on his own. Okay, so we've got the orientation. Now let's read this thing and figure out how many ohms of resistance it has. Remember, we're looking for a resistor with 1000 ohms. The first stripe on the left represents the first digit. So the color of the first stripe of this resistor that I chose at random is brown, and that corresponds to the number 1. Okay, so I know this resistance value starts with the number 1. Second stripe. This one is black. So looking at our chart, this corresponds to the number 0. So now I know the first 2 digits of this resistance value are 1 and 0, meaning that this resistor could be 10 ohms or 100 ohms or even 1,000,000 ohms. We don't know yet. What tells us? The multiplier, the third stripe. Wait, so if we're seeking a resistor of 1000 ohms and we know that the first and second digit are 1 and 0, like, is it possible that I chose at random the right resistor? Am I magic? Let's find out. Come on, big money, big money.
In the next 60 seconds, you could become a millionaire.
So the third stripe is red, which corresponds to a multiplier of 10 to the second, or 100. So I take the number from the first 2 stripes, which is 10, 1, 0, and I multiply it by the multiplier 100. 10 times 100 is 1,000. 1,000 ohms! I won the lottery! But wait, what about the 4th stripe? Well, that guy represents tolerance. It tells you how accurate your particular resistor is. But we really don't have to worry about that guy yet. That's only for advanced electronics, so let's just focus on the first 3 stripes. Back to winning! Okay, but we haven't really won yet. We haven't seen how this 1 kilo ohm resistor behaves in our circuit. Let's see what it does to the light. Okay, I've built the circuit, and this is what the light looks like with a 1000 ohm resistor. We're pretty close, but I'm picky. I want this light to be a tad bit brighter, which means I want slightly less resistance to allow more current to run through. So let's play the lottery again. I'm gonna choose 3 random resistors, but this time I want you to decode them. And then you're gonna tell me which one is gonna give us our desired result. So this one is brown, black, orange. This one is orange, orange, brown. And this one is brown, black, brown. What are their values? Go ahead, I'll wait. Okay, here are the answers. And I'll show you right now an easier way to decode the multiplier. Brown, black, orange is 103, so we can look at this as 10 with 3 zeros at the end, so 10,000 ohms. Orange, orange, brown is 331, so 33 with 1 0 at the end, 330 ohms. Brown, black, brown is 101, so 10 and add 1 0, 100 ohms. Now let's play Goldilocks and plug all these resistors into our circuit and see what the light looks like. I say Goldilocks because I can tell from the numeric values that one will be too high, one will be too low, and one will likely be just right, just under our original value of 1000 ohms. So first, 10,000 ohms. Using Ohm's law, we can see this yields a current of just 0.5 milliamps. And boy, does it show. You could tell me this light is on and I wouldn't even believe you. This resistance is way too high. Useless! Now, let's try the 100 ohm resistor. As you probably guessed, this is gonna let way too much current go through. 50 milliamps to be exact. This light is way too bright to be an indicator, so no, this is not going to work for me. Not in the morning. And now finally, we come to our solution that's going to be just right, hopefully. The 330 ohm resistor. So let's plug her in. Big money. Give it a jiggle. Using Ohm's law, we can see that this current comes out to 15 milliamps. Yeah, I definitely like this light a lot better. Very nice. I like that a lot. So, to recap, balloons make a great analogy for circuits. Voltage is like the air pressure inside this balloon, current is like the air escaping from the balloon, and resistance is how hard I'm squeezing this balloon's neck and preventing air from escaping. And we can use Ohm's law, one of the most important rules of electricity, to relate voltage, current, and resistance. The color bands on a resistor are a code that you can use to determine how much resistance that resistor has. And we can use a combination of this code and Ohm's law to determine which resistor is best for our circuits, like building an LED circuit. And speaking of LEDs, our next video is going to be all about them. Tune in to our next tutorial. Thanks for watching.